I'm Krishna Chaitanya. Today, as a part of the science project presentation, I will be explaining about 4 topics. They are Hermite's polynomial, Laguerre Polynomial, and moment of inertia matrix, and applications of Lagrangian and Hamiltonian mechanical principles in reducing the rocket science equations. Now, I am going to explain about Hermite's polynomial. Hermite's polynomial belongs to the class of classical orthogonal polynomials. If you consider Q and L to be two constant polynomials from R to R, two given polynomials from R to R, then function f of n from R to R, a polynomial f of n from R to R satisfying the condition that Q into f double prime plus L f prime plus some constant C, which can vary over all possible ranges of natural numbers, into the function is 0. The solution of this is nothing but an classical orthogonal polynomial. And the Hermite's polynomial was initially studied by Laplace, which was later scientist named as Chebyshev has extensively worked on this, and finally the improvisations were done by Hermite and it was brought to the state as known today, and hence it's named after him. And now if we move into the equation, the equation is Hermite polynomial of x, nth Hermite polynomial of x is nothing but minus 1 whole power n into e power x square into nth derivative of e power minus x square. Now if you take n as 0, it turns out to be 1, and when you take n as 1, as it is very evident from here, it comes out as e power x square into minus 2x into e power minus x square, which is nothing but 2x. Similarly, you have all the you have Hermite's polynomial defined for all n's. Now this has very wide range of applications, Hermite polynomial, in different fields of science, and there exist different dialects of the Hermite polynomial equation depending on the field of application. This is the equations which we are considering in this presentation. All of them pertain to quantum mechanical applications. The gist of the equation in all the applications is same, but small modifications might be done depending on the field of application. Now we also have a recursive equation for the Hermite's polynomial, which is nothing but hn plus 1 of x is nothing but 2x into hn x minus hn prime x. And since this is an orthogonal equation, it should also satisfy an orthogonality condition, which is nothing but integral of minus infinity to infinity hn of x into hm of x into e power minus x square dx is equals to root over pi into 2 power n into n factorial dou of n comma n, where dou of n comma n is the standard delta function, which is 1 when n equals to m and 0 elsewhere. And if we come to the application part of the Hermite's polynomial, it's applied in probability, combinatorics, numerical analysis, and also the major application which is pertaining to the course is getting eigenvalues of quantum harmonic oscillator. Now I am going to explain about Laguerre polynomials. About Laguerre's polynomials. Laguerre's polynomials also belong to the class of classical orthogonal polynomials, which we discussed earlier. And these Laguerre's polynomials were brought into limelight by a famous French mathematician called Edmond Laguerre. It has its applications in complex analysis of mathematics and also in quantum physics. Now coming to the equation of Laguerre's polynomial, where x, if you consider x comma y as any polynomial functions, then any equation satisfying xy double prime plus alpha plus 1 minus x into y prime plus ny 0, where alpha is arbitrary and x comma y are polynomial functions, is a Laguerre polynomial. Now for the first few Laguerre polynomials are L alpha of 0 of x is nothing but 1, L1 alpha of x is nothing but minus x plus alpha plus 1, L2 alpha of x is x square by 2 minus of alpha plus 2 into x plus alpha plus 2 into alpha plus 1 by 2, And similarly, we can also get conclusively all alpha n, ln of alpha of x using the equations. Now there is a recursive equation to get the Laguerre polynomials, which is nothing but L n plus 1 alpha of x is equals to 2k plus 1 plus alpha minus x into L alpha of x minus of k plus alpha into Lk minus 1 alpha of x the whole divided by k plus 1. And we also have an explicit method of getting L alpha of x, which is nothing but the summation of k is 0 to n nck into minus 1 whole power k into x power k by k factorial. Using this, we can get all alpha n power x using this formula, and also you can use the recursive formula to get the various x's. And this essentially satisfies the orthogonal equation condition basically, as it belongs to the classical orthogonal family of polynomials. And the equation satisfies integral 0 to infinity x power alpha into e power minus x, which is nothing but the testing condition of the function associated with orthogonality, into ln of alpha of x into lm alpha of x dx is equals to tau of n plus alpha minus 1 by n factorial into del of n comma m, where del of n comma m is nothing but the Dirac delta function which we have discussed earlier. Now, if you come to the applications in light of the current course, we see that while solving in quantum mechanical model of hydrogen atom, the radial parameters are got for hydrogen atom in quantum mechanics by using Laguerre's polynomial. This is a major application in light of this course. Other than this, it's also applied in complex analysis in mathematics. Now I will be explaining about moment of inertia matrix. Talking about the moment of inertia matrix. What is a moment of inertia matrix? Moment of inertia matrix is nothing but it's a matrix consisting of all the scalar moments of the inertia when the rigid body is treated as a system of particles. Now we see what is a parallel access theorem. Let us say you want to find a moment of inertia about a fixed point whose position vector is given by r, and let us say center of mass position vector is given by c. Now the moment of inertia matrix of about r will be nothing but minus of summation I is equals to 1 to n1 mi into ri minus r the whole square, where r is the position vector of the ith particle, and we can also say that ir after simplification will come out as IC minus MD square. And seeing the now we will see inertia, moment of inertia about any random axis. Consider IL. Let us say you want to find the moment of inertia matrix IL about any random axis which is passing through a point with a position vector r, and also it's along the vector c. Then the IL will come out as S into minus summation of I is equals to 1 to n mi into delta Ri whole square, where delta Ri is nothing but Ri minus R, where R is the point of axis of consideration, into S, that is equals to S into IR into S, that is equals to ST into IR into S. Now we will see what the perpendicular vector, if you consider a particular Pi, what the delta Ra perpendicular, that is a vector perpendicular to change, will be. That is nothing but Ra minus R, which is nothing but delta R minus S into Ra minus R into S. That is nothing but the moment of inertia matrix I minus S into S transpose, the whole thing into the delta Ra matrix. Now if you do the mod Ra the whole square, that comes out as minus S into delta Ra into delta Ra into S. Now IL is nothing but S into summation of I is equals to 1 to n mi into delta Ra the whole square into S, that is S into IR into S, S into IR into S, that is S transpose into IR into S. This is proved. And now we see the applications. This has applications for finding out the angular velocity, angular momentum, and kinetic energy of the particles about an axis, and we can also find moment of inertia about many different axes. And also the major application which is in relevance to the current courses, it can be applied to analyze the mechanics of a spinning top. That's all about it. Thank you for watching the video.